Hello, Houston. We were right in the midst of trying to demonstrate some aspects of short-term memory last time, and we didn't have enough time to do a demonstration that I want to start here pretty quick with. But as a reminder, let me just go back over a little bit of what we were talking about last time for you. Put on screen what we're dealing with here. And in essence, you will remember then that we were talking about short-term memory, and specifically what I did was to give you several different types of information coded or boxed or chunked in a variety of different ways. First of all, I just read you the letters straight out at about 1 a second, and then what I did was to cluster them randomly and create different kinds of chunks, and then I gave them to you in clusters of 3. And as you'll see, it's the same letters in every instance, but the difference is that you see it, it's much easier to remember when all you have to remember is 5 chunks: TWA, the airline, X-airline, IRS, and so forth and so on. Now today, we're going to give you the toughest one, okay? Whoops, that's not it. You have a block of information in your Cognitive Psych, the book, and I'm going to ask you to remember, I'm going to read you numbers and then say, or I'm going to, let's see, if I'm going to read it to you orally, I'll nod my head when it's okay to, so we'll put me back on the screen full blown, and what I will do is vocalize numbers to you. I'm going to read them to you, and then so as not to provide a cue that overloads auditory loop for you, what I'll do is nod when it's okay for you to recall. You're not to write when I'm reading the numbers, you're only to write after I've nodded my head, okay? It'll be easy at the beginning. Feel when you begin to get a little tighter, okay? So we're going to go down through the list A through L. Here we go. 5. I hope that's not too tough for you. 8, 3. 7, 2, 4. 9, 1, 0, 6. 6, 5, 0, 3, 2. 8, 7, 4, 2, 1, 9. 3, 0, 5, 4, 9, 6, 7. 5, 1, 8, 3, 2, 0, 7, 4. 5, 8, 9, 5, 1, 2, 4, 3, 0. 3 more. 1, 7, 4, 2, 8, 5, 0, 2, 6, 9. 2, 9, 4, 7, 0, 5, 8, 6, 1, 3, 7. 'And finally, 8, 3, 6, 0, 4, 7, 9, 2, 1, 5, 4, 6. Okay, now we're ready. And I was just, I realized that in looking at the information I was about to put on the screen for you that I didn't have the answer key that I wanted to give you next, which is not this one, but this. You want to check your answers and see how well you did? That's the actual set of numbers that I read to you. Just take a couple of minutes to do that, but I'm sure you will be willing to agree pretty rapidly that you probably started having trouble by about halfway through the list. Somewhere around letter G was when you began to panic a little bit, breathe a little harder, have a little more difficulty with it. Now we're going to try one more, okay? And in this case, while you're checking that, I'm going to have somebody else read a number list to me. And in this case, you'll see that it's going to be even harder to remember than the 10 varied numbers that you were given in different orders. You want to go ahead and try it?
1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1.
Okay. I will recall those for you in that order in a couple of minutes. Okay? No rehearsal, just doing it that way. So, in essence, now let's go back to the screen just to be reminded what you're scoring on yours. How many of you got number 5 correct? E correct. 5 letters, 5 numbers in the correct order. About half, 2/3 the hands go up. How about 6? 6 correct. About 1/3 of the hands. How about 7 correct? Got about a half a dozen hands up in the room. How about 8 correct? And there are 1, 2, 3, I see 3 hands in the room. 4. How about 9 correct? 3 in the correct. How about 10 correct? I see 1 hand. 11 correct? Hand goes down. Anybody get all 12 correct? 10 is pretty impressive, I must say. Okay, that is the traditional way of measuring length of short-term memory. And if you do it that way, George Miller's number, plus or minus 7, the magic number 7, plus or minus 2, comes up pretty predictably as the number you'll get correct. Excuse me, but let me show you another way. Instead, what we're going to do is to use a number coding system like this. We're going to chunk the information, in other words, okay? And so in essence, the number sequence that he just read to me would probably have given us a sequence, and let me see if I can remember it correctly. It would have been 1, and you'll have to check off the answer key there to see if I do this correctly. 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 0. Did I get it? I'm not perfect. What did I miss? The last 2 sequences. Okay, then it should have been 0, 1, 0, 0, 0, 1. Okay. What I was doing was taking those units of zeros and ones, which would be impossible to remember if you didn't use some kind of a coding system, and I was using the rule system on the screen, because those are in essence binary codes indicating the numbers 0 through 8. And so basically, I was listening as he was doing that and converting it into the number sequence 5, 4, 7, and I screwed up on I must have made it 2, 1 instead of 1, 2, or the other way around, whichever it was. I had the sequences correct, but they were out of order. And so basically there you can see that in that very simple set of memorization and listening carefully and coding it to a number, each time he read me 3 digits, I was collapsing it to 1, which was easier to remember than just ones and zeros, and expanded my memory to, well, I got 9, I guess, if you want to say I didn't get the last 6 correct. But I jumped from 7 to 9 in terms of number that could be done in that way. In essence, what we're doing in that situation is simply this kind of a sequence. I take the 101 and make it a 5, the 100 and make it a 4, the 111 and make it a 7, and then what I should have done was to take the 001 and make it a 1, and the 010 and make it a 2, and I guess I did, but I transposed them when I was trying to remember it later. The interference there probably came from the fact that I had a telephone number in many years ago that ended in 54921. The 7 I got okay, but I reversed the 2 and the 1 based on old time's sake there. But in essence, what we're doing in that situation is chunking, okay? And we're going to define chunks essentially as a well-learned cognitive unit that is made up of a small number of components representing a frequently occurring and consistent perceptual pattern. And so basically when we use that translation code that I was talking about before with the 1s and O's translated into the decimal system instead of the binary system, it makes the units become a little bit larger, and each unit that I had to remember, 5, 4, and so forth, represented a larger number of numbers. So the 5, the 4, and so forth in my system, and it's not unique to me, were essentially chunks. They were information units where I could remember the chunks and use that to expand to the full material that I was trying to remember. The earliest work on this goes back quite a ways. A gentleman by the name of de Groot actually studied chess players, and they used chunks in an interesting kind of ways. But in essence, what de Groot tried to do was to compare novices and how they would look at a chessboard and retain it, or try to retain it, as opposed to how expert chess players would look at it. And the primary difference is basically in the ability to view or encode the chessboards themselves. That is, what the experts have is the ability to chunk play pieces around the movements or the kind of ways in which they would likely to position themselves in a given game. And so the primary differences between experts and novices is essentially their ability to take larger clusters of the information and group them and remember them as a unit, as such. And in essence, what happens is that at mid-game, after a game has unfolded by some kind of logic, there is a logic to the pattern. That is, there's a reason why pieces are in particular places or not in other places. Because as you know, the queen can move any direction, so she tends to be isolated relative to other people, the other person's players, I should say, and so forth. So in essence, what de Groot did was to view a game of 20 moves. He had experts and novices look at a top-down view of the chessboard with all the players listed, 20 moves into a game played between experts. So the pieces had moved some significant degree of distance at that point. And in essence, what he did was to give a novice and the expert 5 seconds to look at the game pattern, the board, and then remove it. Kind of like the example we were using the other day, 5 seconds to look at 8, 16, 32 pieces, unless some have lost, but some number up to 32 is not enough to know by position where each of them is. And so in essence, what happened then was that he removed all the pieces, gave them to the players, and said, put them back. So the novices and the experts then had to take those pieces and reconstruct the entire board. And what he did, each trial was when the player said, or the person being studied said, I'm finished. And then what he would do is to remove any of the errors. So he left the pieces that were in proper position and then removed only the pieces that were in error. So the feedback was essentially, here's how much of what you originally looked at you've now got correct. And they were allowed to do that through 12 cycles. So 12 times they tried to reconstruct the board, and then de Groot removed any that were not in the correct position and gave them back to the participant to do again. Experts were correct 90% of the time the first time. Okay, I should put that the other way around. The experts the first time were 90% correct. That is, they had 90% of the pieces on the board in the correct position. The novices were 40% correct on the first cycle. The interesting is that from that point onward, when it became a guess in the remaining cycles, the experts were only somewhere between 3 and 10% better than the novices in guessing where the pieces should be, even with their knowledge of chess rules beyond that particular point. And so their superiority in that particular task is based predominantly on their ability to chunk larger units of the players. And when they could chunk larger units, they could then lay out as many chunks as they could remember and do better in recreating the situation. Herbert Simon picked up on that and extended the study to examine the chunks themselves. That is, he used essentially the same procedure and measured the number of plays inserted in time intervals separated by 2-second pauses between each chunk. Okay? And in essence, what he found was that the experts could retain 7.7 chunks on average, that is, subunits of the entire board. Class A players, not quite as good as experts, could retain 2.1 chunks, and the novices could retain, whoops, I've scrambled the figures here, let me start again. The experts could retain 7.7 chunks of information. The Class A players could remember 5.7 chunks, and the novices could remember 5.3 chunks. So even the ability to internally organize the chunks was reduced in the novices, and it cut the number of chunks that they could actually retain in that situation. The chunk size also varied, average number of pieces in a given unit as they were constructed. For the experts, it was 2.5 pieces on average. For the Class A players, it was 2.1 units or pieces in a given chunk, and for the novices, it was only 1.9. So by gaining experience with the pieces, that is, having played chess previously, you had two effects. First of all, it increased the number of pieces that a player could logically connect and remember as a unit, and secondly, it increased the number of units per se the number of pieces of information within each unit that he could retain. So there's a lot of emphasis in that kind of study on capacity and on the factors that lead to forgetting. That in turn leads us to a particular look at verbal information. What I want to do is to look at it in a couple of different ways, auditorily, visually, and so forth. If we look first of all in terms of acoustic codes, basically what we have, the chunks we've just defined for you. Now what I'm going to do is to look at acoustic codes. And recent work has basically emphasized how information is encoded. One of the ways we do that, obviously, is simply by listening. If you're not looking at the screen, then you're encoding, if you are, whatever I'm saying only in the acoustic mode at that particular time. And in each of the demonstrations that we've used up to this point, the emphasis has been on acoustic rehearsal. You have verbally gone over the material as you were trying to remember it. You're saying something over and over to yourself with the intent of trying to remember it. So if we look at those acoustic codes, that becomes the focus of our interest. And one of the things that we find there is a rather interesting problem. A group of investigators, Schweikert, Guntert, and Herzberger, in 1990, noted that what do those letters share in common? Okay, G, Z, D, B, P, V, C, and T share one feature in common. What is it? Mumble, mumble.
It has an E sound.
Yeah, each of them ends with the E as the sound. On the other hand, another group which is easier to remember, letters of this group, M, J, Y, F, H, R, K, and Q, are easier to retain. The difference is that acoustic confusion is much more likely to occur among the first set of letters than among the second, because the second row does not share such a feature in common. That is, they are different in initial sound, if there's a middle sound, in middle phoneme, and also in the end sound. So that basically what we would predict is that the most common error made in spelling, well, let me ask as a prediction, what do you think is the most common error made in spelling my name? Actually, that is the second most common, that they will start with a C instead of a K. But interestingly enough, the most common misspelling is to make F instead of S as the third and fourth letters. because F and S, except for the trailing, sound very similar. And unfortunately, when you do it on phone, F and S sound even more similar to each other than they do when we're just enunciating them to ourselves. But in essence, the tip there goes to letters like M, Y, J, and so forth as being more easily distinguishable from one another. And so in essence, in that situation, we can construct some rather interesting kinds of experiments. For instance, I think Conrad studied acoustic confusion by asking subjects to recall 6-letter sequences. And in one of the groups of letters that he drew his stimuli from was this first set, B, C, P, T, and V, which share as the previous set, E as the final sound on it. And in the second set that was used was F, M, N, S, and X. The difference there being that each of them begins with eh, okay? F, M, N, S, X. Okay, and then what he did was to show 6-letter sequences like this. 75% of the errors when trying to recall sequences like you see at the bottom of the screen there tended to come from the same letter set with which the other letters are paired. So that if S is the one you're looking at, the confusions when they occurred tended to be F, M, N, or X. Whereas if it's V, you tended to get S, C, P, or T as the error in that situation. Such errors really demonstrate the important element of acoustic codes in short-term memory. So there are 26 letters in the English language. How many sounds are there? On how many sounds is the English language actually based? What I'm talking about here are phonemes, which we're going to talk about in more detail later. But how many sounds is English actually based on? In the low 40s, about 42 or 43. So we have 26 letters, but as you know, each of those letters can be pronounced under different circumstances in a variety of different ways. E can be or E or A, and so forth and so on. And so in essence, what that leads us to then is studying words like this. How many of you, by show of hands, and do not say it out loud, know for sure how to pronounce this letter sequence that's on screen now? How many of you know for sure how to pronounce what this word is? Okay, so there's one person in class, 2 maybe, that know the meaning of that word. So those 2 and I could have a conversation using that word, and the rest of you would be fishing through your entire memory looking for the nature of the word itself. And yet in the last 30 seconds or so, I have actually pronounced a variation of that word in my language. Okay? So in essence, it is there. The word is actually pronounced how? Make sure you get on mic.
Fish.
Fish. Yes, of course. It is fish. Say it isn't so, you're mumbling to yourself. Well, it is. GH is pronounced how in TOUGH? Yeah, like an F. It's not pronounced tough. That's T-O-U-G-H. I asked only how G-H is pronounced in T-O-U-G-H. So there's our F sound. How is O pronounced in W-O-M-E-N? I, yes, as in women. There's the I sound. How is T-I pronounced in E-M-O-T-I-O-N? Shh, that's right. So there we have it. Add those phonemes all up and you have fish. Fish. So G-H-O-T-I is pronounced fish. Now, I'm obviously breaking some rules there. For instance, in English, GH is almost never the starting sound of a word except in words like ghetto. And there it's pronounced G or getty and so forth. So the G sound is not normally pronounced that way if it's at the beginning of a word, but it is in this case. I've simply taken another variation of phonemic stress or pronunciation and used it in that case to create a kind of a game word, a word that is spelled actually based on sounds rather than the actual sound that we normally associate with it. And in fact, if we can take my picture off the screen there for just a second, what you're seeing there is a sample of what's known as the International Phonetic Alphabet, which is an alphabet of sounds. Okay? And in that sequence, the NJ symbol then is used to produce the ng sound, as in wrong or anger. Okay? The tipped over S is the sh sound. The theta is used to indicate thin, or the th sound, or tooth. That's the same phoneme in that case. Whereas the backward 6 with a slash is the same sound, th, but the difference is it's vocalized. So if you feel your vocal cords when you say tooth and hold the last sound, your vocal cords are not vibrating. But if you say breathe and hold the last sound, in that case your vocal cords are vibrating. So the mouth is shaped the same in both cases. In one instance it's also got vocal cords vibrating, in the other instance it doesn't, which produces a different sound, phoneme, and therefore we need a different symbol to represent it in the International Phonetic Alphabet. My name is spelled out below there in the International Phonetic Alphabet, or IPA symbols, which would tell you then there are two things missing there. One is the relative stress, which is normally encoded by a superscripted 1, 2, or 3. So whatever is the highest, the most emphasized phoneme in a particular word has a higher number associated with it. And the timing is illustrated by the spacing which is there. So in that, what you would suggest is that in pronouncing Richard, the greatest sound is, the greatest distance or length between phonemes is between the end of the ch and the start of the in Richard, okay? But in essence, that is sounds produced in the International Phonetic Alphabet. And thus it turns out, as I said earlier, that if all of the letters in the BCP-TV combination have the E sound at the beginning, and the FMNSX have the eh sound at the end. Ken Lockery did a rather interesting study based on that, based on a very simple assumption. What he asserted or assumed was that basically you could forget letters. If you were asked to remember a string of letters, for instance, what would happen is that you could forget, if a letter is stored not as a letter but as phonemes, you might very well forget a phoneme within a letter and not forget the entire letter. So if you were trying to remember S and all you could remember was eh, then it's logical that the errors that you might guess would be M, N, and so forth. Okay? So if we divide each of the letters down into its constituent phonemes, what Lockery was asserting is when you forget, if you don't forget completely, you may forget the initial phoneme or the final phoneme or a middle one if there are three. And thus what that does is to constrict the letters from which you guess if you can't remember the entire letter as you were doing it. And it turns out that different phonemes are forgotten at different rates. That is, if you've forgotten one part but remember E for the last letter, those are the kind of letters that you're going to, you're going to demonstrate, you're going to utilize. And in a later discussion, what we're going to do is to return to consider the role of acoustic processes in things like reading. Not today, but in a later letter, in a later lecture, I should say, where basically what we're doing there is converting visual cues or letters into auditory codes. When you're reading out loud, what you're looking at is visual codes, and you're converting them into acoustic codes, which in turn leads to another process that is quite interesting, and that is the role of pronunciation time. It turns out that instead of remembering 3 chunks of letters, as was true with the Peterson's work, Murdoch replicated Peterson's original work doing like ZAM and then a time sequence and then asking to recall it. He did it using words instead, simple 1 or 2 syllable words, and he found that he could replicate the recall cues or the recall data very precisely. That is, if you'll remember, the Peterson's curve dropped to about a chance level in about 18 seconds if you weren't allowed to rehearse 3 letters. Well, Murdoch was able to demonstrate that in the same form using words, 3 short words instead of letters. Schweikert and Boroff in the mid-'80s tested memory in a wide variety of different types of items, from nonsense syllables to nouns and numbers and consonants, as well as the names of various shapes and colors. And what happened was a very consistent finding, and that is that what they discovered was that you and I remember, in a sequence that we're not familiar with, about the first 1.5 seconds of what we hear. The first 1.5 seconds of what we hear. And what that led them to develop is what's called the pronunciation time hypothesis. Okay? And in that situation, What you do is in one of the tests that I'm going to show you here is I'm going to, in just a second here, I'm going to put 6 state names on the screen, okay? I want you to read them off out loud as rapidly as you can, okay? And then if you're done, I'm going to take the screens off the screen, and as soon as that's done, then I want you to try to write down or recall as many of them as you can, okay? Do that silently because I don't want you mumbling the answer to other people, okay? So 6 state names are going to come on the screen. I want you to read them out loud as rapidly as you can, and then when everybody's done, I'll take them off the screen, and at that point you should recall them. Write down as many as you can, okay? Here we go. California, Pennsylvania. You don't have to write the whole thing, you can abbreviate them. Now, I'm going to assume you're mostly done. I'm going to do the same thing, different state names. So again, when they appear, you're to read them off as rapidly as possible. When they disappear, you can then write down as many of those as you can remember. Are you ready? Utah, Maine, Kansas. Okay, how many of you got 6 out of 6 of the long named states? How many got 5 out of 6? Okay, no hands went up with 6. About half a dozen, 10 maybe went up with 5. How many got 4 of the long named states? Okay, and again, a majority of hands are up. How about on the short named states? How many of you got 6 out of 6? 1, 2, 3, 4, okay, half a dozen, almost a dozen. Okay, the point is, as it should be obvious, that you can read those 6 state names a lot more rapidly than you can read the long named states. Okay, the short named states you can read through much more rapidly than the long named states. And so what the presentation time hypothesis is suggesting is what we've just demonstrated, and that is that you will not be able to remember as many of the 6 when the names are very long to pronounce, when it takes a long time. With short names, you can do it. It turns out the same effect also works with nonsense syllables. If you can recall about 4 nonsense syllables, but numbers, which in general are much easier to pronounce. Nonsense syllables are usually consonant vowel consonant combinations like ZAM that we were talking about. But you can say 1, 2, 3 faster than you can say ZAM. And the prediction then is that you would be able to remember numbers better than consonants, and that does turn out, and nonsense syllables, and that does turn out to be true. That in turn leads to a cultural comparison, which is rather interesting. And that is that if we look at this data, I will show you on screen here the data first and then explain to you how the study was actually done. This was done by Nave, Benjamin, and Ayers back in the mid-1980s. And basically what they did was to look at the languages along the bottom there, English, Spanish, Hebrew, and Arabic, and actually count or time how long it takes to count from 1 through 10 in that language. English, it turns out, is the fastest of those 4. It's the most efficient one because, with one exception, all of its syllables, all of its numbers are 1 syllable. 1, 2, 3, 4, 5, 6, 2 syllables, 7, 8, 9, 10. So you can actually count, and on the right side there, what you see is the presentation rate in terms of items per second that you can go through English. In other words, you can count, you can try it later at home, but if you count from 1 to 10 twice, it takes you just about 5 seconds to do it if it's legible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, and so forth. Takes about 5 seconds. Dividing in half, that's 2.5 seconds to do 10, which means it's about 4 items per second that you're going through. Does anybody in here speak Spanish well enough to just count to 10 for me? Can you put on the mic and just count in as rapidly, at least as I was doing, 1, 2, 3, 4, count from 1 to 10 in Spanish?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, I should have timed it, but my hunch is, and what the data suggests is that it's about 60% longer to do Spanish because some number of the numbers are 2 syllables. Okay, which just lengthens the length of time it takes to say them. I mean, mathematically, we're just as good either way, but the language is longer. Hebrew is even longer. Does anybody in the room speak Arabic? Okay, well, the Arabic numbers are up to about 2.5 syllables on average. And so what happens again is that you see that the pronunciation rate, the number you can say per second, drops down to, with Arabic, you're only at about 2.7 in counting from 1 to 10 that you can cover. On the left side then, what you see is the memory span of what can be retained as a function of which language you're counting in. Okay? And what is demonstrated there then, that is in English, you can on average, there's George Miller again, remember 7 digits because they're fairly easy to say, single digit apiece. And with English, with the shorter signal basically for each number, you can load more, you can hear more in 1.5 seconds than you can if you're speaking a language that has multiple syllables for the numbers. So in essence, the pronunciation rate per syllable or per number drops as the number gets longer phonetically, and memory also drops because you can't, in the same 1.5 seconds or whatever that number actually is, retain as much information in that particular situation. So in essence, what we conclude is that pronunciation rate impacts short-term storage capacity, short-term memory, as well as chunking. The ability to chunk number sequences into given size units is reduced as the magnitude of the number grows in length, which in turn then puts us into another factor that I also want to look at, and that is semantic similarity. So far, what we've done is to stress simply the size of the chunking, the size of the stimulus or the chunking, and the sounds that are being utilized here. Now let's look at it another way. Let's examine instead the impact of semantic relations among words that are to be recalled. The classic study on this was done by Delos Wickens and his colleagues way back in the mid-1970s. And to discuss what was done, let me anticipate a concept that's going to become relevant here that we're going to examine a little bit later, and that is interference. And I'll show you why that's relevant here in a couple of minutes. But interference, many would argue, is the primary basis why we forget. Okay? And so in essence, we're going to start with this kind of a sequence. We're going to have something that we learn originally. There will be some interval of time during which we are to retain it, and then there will be a test as to how accurately we can recall what we've learned earlier, okay? So we have original learning, a retention interval, and then a test of original learning. For the purposes of describing this, what we're also going to put in there is earlier learning. That is, at any given time you and I start learning verbal materials, we are not naive. We already know the language we're studying and have worked with it a great deal. So there is earlier learning with almost anything I would give you now in order to have you learn. And in essence, then, what we're going to argue is that proactive interference, which is one of the types of things that could hinder our ability later to recall that original learning, is any time and effect anything that you've learned previously hinders the subsequent learning that you do. Okay? We're going to define proactive learning then essentially as indicated there on screen, and that is forgetting of information due to the effects of previously learned information. That's proactive interference. Any learning you've done previously acts forward in time to hinder later learning and your recall and demonstration of having done that learning later. So it's forward acting in time. In the model here, there is, however, another sequence that can also exist, and that is stuff that you do or learn during the retention interval may in fact hinder your ability to recall that original learning a little bit later. That is what is called retroactive interference. And we define that as forgetting of information due to learning that intervenes between the initial experience and the eventual attempt to recall. Okay? That is retroactive or backward-acting interference. For now, I'm only going to concentrate on the forward-acting interference, and I'm going to suggest the following kind of an example. Let's suppose that you spoke and studied Spanish up through high school. Now that you're here at the U of H, you have been mastering German. You've decided to study German as a language, okay? All of a sudden this Christmas or next summer, you have the opportunity to go to Berlin. And the question then is, when you're reaching for that German, which language is going to leap to your head when you're trying to order a hot dog or ask for where the men's or women's room is? Okay? That is one way in which we can test for proactive versus retroactive interference. And what we find in that situation is that if you know one language previously learned, one language subsequently learned, which you're trying to recall after you've studied yet another language, the errors mostly come from the earliest language. Okay? So in that situation, if you did have trouble in Germany recalling the German you'd been studying here at the U of H, it would be Spanish which would tend to jump in and hinder you if that was also studied as a language in prior times. Okay? We'll come back and look at that in more detail a little bit later. But in essence, what's illustrated there is the phenomenon related to what is called proactive interference. Now, that type of study led to a very interesting effect, and that is what is called release from proactive interference. And in essence, what we've got there is a rather interesting phenomenon. Specifically, if you learn something and then learn something else and then learn something else and then have to recall that something else. My hand is off the screen here now, but if you've got 4 trials of information that you're trying to learn, if all 4 of those pieces of information are identical or of the same type, your recall by the 4th time is subject to that proactive interference. Okay? Keep that in mind when we look at a demonstration of release from proactive interference. And again, I'm going to show you a graph here that shows release from proactive interference in the following way. Okay? What we're going to plot on this graph is trials of recall efforts on different types of stimuli. I'm sorry, on one type of stimuli, as I'll show you here in a minute. And what's going to be plotted is simply the percent of correct responses that we have. Okay? The learning using, first of all, only fruits was as follows. On trial 1 with a list of fruits, we had about 90% correct recall. On trial 2, you can see it's down to about 40%, and by trial 3, we've dropped into the mid-30s somewhere in terms of the percentage of items on trial 3 list that can be recalled. Now look at what happens when we do fruits on trial 4. The decline continues. Okay? You've studied fruits on trials 1, lists of fruits on trials 1 and 2 and 3, and performance is dropping, reflecting proactive interference. If we give you a 4th list of fruits, performance continues dropping. By now we're down to just about 30%, not even the low 30s. We're down to maximum 30% recall of the 4th list after 3 prior lists. But look at what happens as the semantic distinction between the first 3 lists and the last one grows. The next curve up is what happens if you have 3 lists of fruits and then are given a list of vegetables. All of a sudden, whoops, recall is up to about 40%. And in fact, if you're given a list of flowers, it's up to about 50%, it's up to about 45, well, almost 50%, say 45%. If you're given a list of meats as the 4th list, recall is now up to about 48%, maybe crowding 50. And if you're given occupations, which are totally, unliving entirely, totally unrelated semantically, look at what happens to recall. It's back up almost as good as you were with fruits on trial 1. You're up in the mid-80s, almost 90%. What that is called, again, is release from proactive interference. That is, what's being demonstrated there is that as the cognitive nature of the material, as the semantic nature of the words that you're learning changes, as the relationship between them weakens, the interfering effects go away. So it isn't per se the fact that you're getting tired of learning lists of 8 or 10 or 12 items. It is rather the specific content of that which is altered. Which is adversely affecting your performance. So that basically, as the semantic connection weakens, the degree of recovery improves from 25% recall of more fruits after only fruits to 70% recall of fruits after seeing, of occupations after seeing fruits. Okay? I misspoke earlier. I said it was 90. It's up about, it's in the high 70s% when you're asked to do occupations on trial 4 rather than fruits that you've been doing. So in essence, what we can conclude from that is that basically semantic relations can also impact recall. That is, what I'm building here is a case for the fact that short-term memory is not just based on passive storage of information only as a function of time. There are things that can break down or work to our benefit in memory in a variety of ways. So we demonstrated first the impact of acoustic coding. We've also looked then at the impact of semantic differences. And as the semantic distance increases between given groups that you're trying to retain, the recall of that second group is less and less subject to proactive interference. So semantic relations can also influence how productive, how accurate we can be in recall. So what I'm going to do is to summarize the model that we have worked with up to this point and show you the following. In essence, this is what's called the Atkinson-Shiffrin model of human learning and memory, sometimes called the HAM model, or Human Associative Memory Model, that's involved here. And basically what this shows is two of the types of information that we have looked at so far. Sensory store is information which is registered, for instance, on your eye, or you hear it coming inbound, and if you pay attention to it, that information is then input into what we're going to, for now, call activated memory or short-term memory. And in that place, one of several things can happen. For instance, the information may be encoded into long-term memory, and we'll talk about that more later, long-term memory specifically, from which the information can be retrieved. But what this model is going to argue is that anything that you and I interact with is in short-term memory. That is, you and I are actively processing information, and we will see that element of this theory show up in a lot of data that we'll look at later on. For instance, just to give you one kind of advanced tip on one thing we'll look at later in processing language, spoonerisms. When you transpose sounds in two words in a sentence, you get the first part of one word attached to the last part of another word, and you create a kind of a funny nonsense word. When those kind of links occur, when those errors occur, when sounds get exchanged, the exchange word is never more than about 3 or 4 words ahead of the one with which the exchange occurs. In other words, what that's arguing is when spoonerisms occur, that you and I are processing, I'm processing the sentence that I'm in the midst of right now, only about 3 or 4 words ahead of what I'm actually saying, so that the words are being retrieved from long-term into short-term memory and then inserted in the proper place in the sentence, only about 3 or 4 words ahead of ourselves when we're talking, and that's the reason you get that spoonerism effect, never bridging more than about 3 or 4 syllables. What also is going on then in activated memory is rehearsal. That's where you are actively retaining the information, and you may directly output it. As for instance, when I'm doing a demonstration here on screen, I may ask you point blank right then, did you see that? Or do you see what I'm talking about? And the answer then is for you, yes or no, is coming straight out of short-term memory. Or in fact, in some cases, you simply lose it. By failing to continue to rehearse it long enough to retain it in long term, you simply lose it. Alan Baddeley, which is the only person we're going to talk with about for the rest of the lecture here, proposes a very different model. What he's going to essentially argue is that so far we have been talking about, and in fact, let me just talk about the particular study here. What he's going to do is to propose what you'll see here in a little bit is basically a multi-component interpretation of short-term storage. And what it's going to be is an action model, not a passive storage retrieval model. The activity certainly is in the storage and retrieval and rehearsal, but he's going to argue one that is even more action-based than that. He's going to hypothesize 3 components, as I'll show you here a little bit later. Why? Well, this study that I'm going to recite here was the basis for the model that he actually proposed in this situation. In this procedure, and we're going to come back to this a couple of times because it's quite complex, so let me go through it once slowly with you and then kind of retain this first part, because this first part is going to come back and show up in another experiment a little bit later. They compound levels upon levels upon levels of activity and then get some very interesting deterioration, sometimes in acoustic processes, sometimes in visual processes, processes, sometimes in something unrelated to either of them, which becomes, when you look at the aggregate of what I'm going to be talking about for the rest of the hour here, very compelling evidence for the fact that it is not just a passive retrieval system or storage system. It is, in fact, a multi-component short-term process that we use here. So in essence, in this particular experiment, what Bailey and Hitch did was to give their participants anywhere from no to 8 numbers to rehearse and recall. They were given a series of 8 numbers which they had to rehearse and be able to recall. In other words, they were trying to learn them, essentially. Rehearse them and then recall them. At the same time, what they were given was a series of statements on screen like what you see now, H follows F. And they were supposed to be analyzing those visually presented statements. So right on the screen you see H follows F. Well, if you know your alphabet, the answer in that case is not true. But you have to process the H and the F and think about the order of the letters in the alphabet in order to be able to hit one of 2 buttons. If the statement that was presented on the screen was true, then you hit the yes or the true button. If the statement was false, then you hit the red or the no button. Okay? So that is the task that you're actively dealing with at the time. Statements, true or false, are coming up on the screen, such as H follows F. And you then have to look at that visually and react to it. All the while that you are simultaneously processing the number list that you're trying to learn. So if you think about it, what's happened here is that what they have actually done in this study very cleverly is create 2 different kinds of tasks. The H follows F true-false task is purely visual. You're reading it off the computer screen and you're reacting manually with the yes or the no button. That's all. So all you're having to process in that case is visual information, task 1. The second task is you're actively rehearsing a list of numbers that has been fed to you, and you're doing that verbally. 713-872-98, 713-872-98, or whatever. I've already forgotten my list, but that's done verbally. Okay, that's an auditory phenomenon that is going on. You're speaking it, yes, but you're listening to it. So that's going on in an auditory manner. The results are intriguing, because basically it would seem that the more numbers that are being rehearsed, the poorer the reaction time would be. Would you not expect? That is, if you're trying to retain 8 numbers in your head and memorize them, you would expect, would you not, that when you're faced with a task like H follows F, the reaction time would slow. Because if you've got a single short-term memory, that's likely what happens. If you're already busy saying an 713-872 number or whatever, if that's loaded, then you start trying to do things visually, you might expect or predict that reaction time would drop. It doesn't. Reaction time actually increased less than 1 second. Okay, I'm sorry, I misspoke. What you'd predict is reaction time would increase. It would take longer. Response time would increase. Okay, that isn't what happened. It increased very slightly, but less than a second from where you were rehearsing 1 number and trying to remember that to where you were rehearsing a sequence of 8 numbers while trying to do the visual task at the same time. Okay, the error rate was essentially flat at approximately 5%. That is, across all the different letter puzzles like H follows F that they were asked to do, the error rate was only about 1 in 20 that was missed, regardless of how many numbers they were reciting at the same time. That is a very difficult set of results to explain in terms of the Atkinson-Shiffrin model. Okay? And so they conclude that basically short-term memory has to be multifaceted. It can't be just a single feature or a single ability operating at any given time. Okay? Miller came up with the idea of 7 plus or minus 2 way back in 1956. Bailey, another 20 years later, essentially, comes up with the idea of multiple components. A very significant alteration in the way in which we are viewing what is called, at that time, short-term memory. And from 1986 through 1999, almost 2000, for 15 years or more, what Bailey and his co-workers did was to develop a 3-element model of what they call working memory. And so this work basically leads to the assertion that short-term memory is not a monolith. or a box, which converts all input into an auditory or verbal visual code. Okay? It doesn't do that. Okay? In fact, what is being proposed here is that the term short-term memory, viewed as a box or a monolith, simply is not correct, and that a much better analogy to use is working memory. And that is the reason that this section of material on screen and the section that we're in here is being labeled essentially working memory. Because as we're going to see in the remainder of the lecture today, basically there are a lot of different things that may be going on and a lot of different ways in which you and I may be processing that information. Okay? It has been proposed then that you might even think of the analogy of a workbench, that instead of viewing short-term memory as a box, you think of it instead as a workbench where you're working a little bit on this and you're working a little bit on that and you're working on a lot of different things at any given time. And so basically what is going to be proposed here is a model with the following kinds of components. The first thing that he proposes is what's called a central executive, which is where limited capacity attention operates. That is, when we demonstrated in some of the earlier studies channel capacity, and the example I used earlier of processing one thing having to be reduced when you're processing a similar thing, that is in essence a problem in the central executive, what Baddeley is going to call the central executive. That's where limited capacity attentive operations are occurring, okay? And it's attached to the central executive in addition to a limited number of other systems that are capable of operating simultaneously, as we just demonstrated with the initial Baddeley and Hitch study. That is, that in that case they had visual tasks going on at the same time that an auditory or verbal task was being conducted. And so basically what Baddeley argues is that future research may even be able to identify other such units. But for the theory as it's originally proposed, it's going to include the following kinds of units. In addition then to the central executive processor, if you want to think about it that way, he is also proposing the existence of what is called, and the labels here are not particularly elegant, the articulatory phonological loop. I might have come up with something a little better than that. Speak and talk, or speak and hear, but in essence that is what he's talking about there. That loop, that element of memory, essentially maintains and manipulates auditory acoustic information. That's where what you're hearing me say is going into at the moment. That's where it's processed, okay? It's prone to sound errors. That is where a confusion among rhymes occurs. That is also where things like puns are developed, okay? Where you know, if you're good with punning, as a limited number of funny people are, then what the processing that they're doing is in this component of short-term memory when they're making a link to develop a pun that they want to offer in a given situation. This unit requires active processing. This is a unit that is constantly active in order to maintain operation. Okay? There's some evidence to suggest that codes in that loop can disappear in as little as 2 seconds if they're not repeated. If it's a complex pattern, only a part of which you're working with, you may lose memory of another part of that pattern simply because you have not rehearsed it in active memory. In turn, what he argues is, and the reason for calling it the articulatory phonological loop, is that there are actually 2 different loops involved there. One of them is the phonological unit. This is the one, in accord with this theory, that processes speech. It operates exactly in the same way that short-term memory does in the Atkinson-Shiffrin model that I showed you a little earlier. So basically what Baddeley is arguing is that entire model dealing with short-term memory is in this loop of the broader theory that I'm developing here in relaying to you what his work demonstrated. The second element then, oh, and again, that's where acoustic errors can occur. In the second element, we then have what is called the articulatory or rehearsal process or loop. Here is where information is stored in terms of its oral or its motor properties. Okay? This is the unit that gets messed up when you start saying something like toy boat and say it over and over and over again. I'm sure you did that as a kid, toy boat, toy boat, toy boat, toy boat. And pretty soon you're doing toy boy, or, you know, it just literally falls apart in your mouth. Okay? That's an example of problems in the phonological component of the articulatory phonological loop. Okay? It also explains some phenomena that are difficult to explain by a strict unitary short-term memory model, as we're going to demonstrate here in a little bit. Now, in essence, what we're now going to do is to, I think I have a demonstration set up here. Yes. I'm trying to remember. This is the problem when you do it, you look at it once and then come on television. The time pressure is pretty heavy on me at the moment. What in essence happens is that if you are listening, this is what I'm going to describe to you verbally. Let us suppose that I present to you a screen of numbers that are coming up, and all you have to do is read them one at a time as they appear. Not hard. Easy numbers, you read them, okay? Once a second, once every 2 seconds, you're doing this. What I am doing while you're doing that is reading to you a list of meaningful words. I am speaking meaningful words to you. Lemon, strawberry, pine, oak, and so forth, at about that rate. What happens is that your ability to retrieve and enunciate the visually presented numbers deteriorates, even though I told you to ignore the words. Okay? So I've set you down in front of a computer, and I'm going to pop numbers on the screen once every couple of seconds, and I've told you to remember the numbers. And at the same time then, in earphones, you're hearing a list being read to you, which I tell you, think of those simply as distraction. You do not have to pay attention to them. I will not be asking you any questions about them. And still, what happens is that your ability to read the numbers and to retrieve them, deteriorates when we add the words. Okay? So your ability to retrieve and enunciate the visually presented numbers deteriorates even though you were told to ignore the words. If we can go back to the screen then, what we have is what is labeled the unintended speech effect. It's there, the effect on it on your performance is unintended, but it's there nonetheless. Interestingly, and here's where you begin to see the complexity of the model that Baddeley is proposing, if we use nonsense syllables, they are just as disruptive as meaningful words. So the disruption is not based on semantic processing of the words. It is simply the fact that the auditory loop is involved. So if we just read nonsense syllables to you, we still get the deterioration in ability to process the visually presented information. But phonological properties are involved. I'm pushing this 7 different ways with exceptions to show you how complex this process is. The phonological properties are involved. That is, the sound of the words coming in is what's causing the hindrance. Because if we just put in white noise, it doesn't hinder it. So it isn't even as simple as, well, it's just that you've got noise in the ear. That isn't it at all. It is the fact that you've got noise in the form of units that you are used to processing. That is what's fouling you up. So again, what I'm saying is, you're reading numbers off a screen. If I add words, your performance deteriorates. If I even add nonsense syllables, your performance deteriorates. But if I add noise, just white noise from an FM radio, it does not deteriorate your your performance. Okay? If you're given one word to repeat over and over again, the unintended speech effect goes away. If you're given one that you can automate and therefore do not have to process, the effect goes away. So in essence, our unintended speech effect disappears if we just give you a single word that you are to say over and over and over again. From that, then, we can reach several conclusions. I've hit you with a lot of data or observations from this study, but let me just summarize it for you. We can conclude, I'm going to argue 6 things. First of all, visual information usually is recoded into the phonological loop, taking advantage of that phonological store. You know, your mother may have mumbled at you, well, you're not supposed to move your lips when you're reading silently. But that's just part of what we just kind of automatically fall into. We're mouthing to ourselves the words as we're reading them. Secondly, spoken info automatically has access to the phonological loop. If it's spoken information, it automatically accesses that phonological loop. Thirdly, any spoken words, whether nonsense or not, also have access to the phonological loop. Fourthly, by removing the availability of phonological duplication, what this does is to hinder the recall of visually presented information. So where normally if we're reading something or it comes in visually, we just automatically hop it over and say it to ourselves or put it in phonological form in some form, some sort. But if that loop is now busy with another auditory task, you can't do that, and that hinders the visual task. Fifth, repeating single word blocks or the entry of spoken words into the let me say that again. Repeating single words blocks the entry of spoken words into the phonological loop. And the effect of that then is point 6, that the executive can utilize the phonological loop for recording visual information, which is aiding recall. That is the explanation for the relationship between the incoming visual as opposed to auditory information. Okay? Which leads then to the second component of the theory, and you're going to have to wipe my picture off the screen here now, and that is what is called the visuospatial sketchpad. They're even further afield in creativity of labeling on this one. Okay? Titling's a bit crude, but what it does is to maintain and manipulate visual and spatial information. For instance, when you're reading a map, as an example, and we'll come back to that for a whole section of the course later on. But essentially what this is going to argue is that if you're reading something verbally, such as la 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 la, okay, it keeps the phonological loop occupied, but it does not restrict use of the visual sketchpad, okay? Like the phonological loop, the visual spatial sketchpad can be overloaded. We can give you too much information and you can't put it all in there. So that like the phonological loop or pad on the left side, the visual spatial sketchpad can also be overloaded. Working problems that are too big for your sketchpad's capacity will lead to errors in interpretation or potentially errors in recovery of information because it was stored inaccurately or it's so complex you don't have enough cues to recall it. There are several different ways in which that can occur. Brooks, back in 1967, designed a task to assess the spatial and the visual and the verbal memory coding. This is when we begin to pile things on top of each other and it becomes a very picture yourself as a subject in this experiment by the time I get done describing it. What Brooks is going to do is basically to design a task that is going to assess the spatial and the verbal memory coding simultaneously. Okay? So we're going to first of all give the subject a series of statements and ask him to repeat them. Simply, they're given to him visually, he has to repeat them. Okay? Secondly, we're going to have verbal and spatial statements that could be converted into a path through the maze. In other words, using the visual sketchpad. An example of what I'm talking about is that if you're standing at the University of Houston and you're trying to imagine how you would go to Galleria, that's something where you might envision, okay, I'm going to go down Cullen until I get to the Gulf Freeway and then turn under it and go toward town or left. In that case, that statement, if I made it as I've just made it to you visually without any visual, as I've just made it to you verbally without any visual description, nonetheless in the minds of some of you was converted into kind of a mental image or maybe even a map in your head of, okay, Cullen, he's going to the Gulf Freeway and turning north, and so forth. That's a case where a verbal statement could in fact be converted into visual kinds of information. And in essence then, the nonsense statements had the same amount of information, but they were non-spatial. So in essence, in some cases he gave visually or graphically obvious statements dealing with things that could easily be encouraged that way or encoded that way. And in other cases he used nonsense statements. But the recoding is much more difficult when you're using a nonsense statement that the words are just randomly scrambled in there. And the results were that the spatial statements presented auditorily, that is by ear, were remembered better than those that were presented visually. Okay? Because since the visual pad had been blocked, they could be remembered better when they were presented orally by ear. It was the reverse with the non-spatial statements. That is, they were better retained if they were presented visually rather than auditorily. Again, what's being demonstrated, a lot of data, but in essence, again, what's being demonstrated is separate demonstration of a verbal or auditory coding system and processing, as opposed to visual information and visual processing thereof. And what you see then is when you keep one busy, if you feed in on the other where it would try to use the one, but it can't, performance is less than when the hindrance isn't there. Okay? And if you feed into a given unit something that already has it busy, when you try to feed in additional information of that type, whether it's auditory or visual, the effect is to reduce the ability to perform that second task when it's overloaded. So that in essence, what we're arguing here is that representing spatial sequences utilizes some of the visual spatial space sketchpad, I keep saying spacepad, which interferes with processing written into it like text. Interference is two-way. It works both ways, input and output. Processing visual stimuli interferes with the visual spatial sketchpad processing of spatial sequences. Okay? The source of interference there is some kind of spatial conflict, some kind of spatially based conflict in the processing. Reading text requires, as you know, that your eyes move through space to be coordinated. That's a visual spatial task, sketchpad task. When I'm reading information off my notes here, that sketchpad is keeping busy about where am I in space, which word is being processed, what's the next one, and so forth. That movement has to be integrated with the incoming, what is basically visual information. But spatial statements also require spatial encoding. And as a result, both tasks then are competing for the use of storage in the visual spatial sketchpad. That's essentially another way of saying what I said a minute ago. Now let's test it. Here is where we really become complex. Bailey, another experiment, asked subjects to track a target visually on a computer screen, okay? While doing the task that we described earlier, that is where you attend to numbers that are being rehearsed at the same time that you're looking at visual letters on a screen. So we've now got words being fed in that you're rehearsing. We've got an image on the screen, and we're now going to add another visual image on top of it. You talk about confusing. That's the experiment that would do it. Okay? Let me put some information on the screen that may help you here. Condition one of what he's going to set up here is a target sine wave, which is simply, you've seen it on medical shows before, a sine wave is just moving across the screen, okay? That's a moving target, okay? The target is moving on the screen, sine wave pattern. Condition two in the experiment he's going to set up now is slightly different. The target is still, but the background was moving. So there was some kind of a striated or patterned background which was moving. And so basically, the movement of the sine wave was apparent, but not actual. That is, if you looked at the sine wave, your eyes didn't move on the screen. What was happening was the background was slipping past it, okay? In condition three in this study, now what we've got is the target and the background are moving. So we've got the target going one direction or one speed, and the background going another direction or another speed, okay? So now we've got both background and target moving. Remember now that the retention task were auditory cues. They were the numbers that were being fed in and rehearsed, okay? That's overlying. And again, do I need to go over this again? You've got numbers coming in that you're trying to rehearse and learn. You've got a visual pattern that you're trying to react to on screen, and you've got now superimposed on it the wave, either the wave's moving, or the wave is still, the background is moving, or the two are moving together. It's a sick mind that created this particular experiment. Okay, the results are basically that since the retention task were auditory cues, we would expect that there's going to be better performance on the spatial task in this situation, and that is exactly what was found. Okay, the findings are basically that when we look at it, 70% if in condition 2, which is the one that's crucial here for the moment, the eyes were fixed and the background was moving. Remember, that was the sine wave here, and the background is shifting back and forth. So in condition 2, the eyes were fixed and the background was moving. And in that case, what we find was that 70% of the spatial sequences were retained of the information on screen, 68% of the nonsense syllables. Okay? In conditions 1 and 3, very different situation occurred. Now what's happened is 52% of the spatial sequences are retained. That has been hindered. But the nonsense syllables are essentially unimpeded. Slight drop, but 63% of them are still being retained. Okay? So that in that particular situation, that is, the eyes were moving during the nonsense task, and that dropped performance 5% from 68 to 63%. When the subject's eyes were moving during the spatial task, it dropped performance 18% from 70% to 52%. The work suggests essentially that working memory is not a single register of information, and it involves at least two cognitively related but independent processes: the auditory processing and the visual processing. I've got a little bit more to say about this, but we'll pick it up right at the beginning of the next lecture about the central executive.